we go. So here, what we're going to look at is what a function is. Now, a function is not an easy concept. I'm going to be honest. It's not an easy concept to understand, but it's one of the most important ones that we do in class. I mean, if you go on to, if you go on to later science courses or math courses, actually, like pre-calc, calculus, you're going to have to deal with functions. It's one of the most important concepts we're going to deal with in this class. It's also one of the toughest, though. Okay. So I do kind of follow the book here, just letting everyone know the way they present what a function is. They use relations, they use correspondence mappings, which I think are very useful because they're very visual. But I will present the definition of what a function is. The definition's really abstract, so if you don't get it at first, don't panic. But it turns out you can get a function using many different representations. For instance, relations, correspondence mappings, which, I will say what those are. You can actually get functions from equations in two variables, x and y. And from graphs also. So we will actually look at that. I don't know if we won't get to equations today, but we will get to relations and correspondence mappings. And from graphs, we actually can, we will also see that is the vertical line test. We will see what that is. You might have seen it before, but if you haven't, that's okay. Again, I'm kind of erring on the side of caution, so to say, where I'm not going to assume you've seen this stuff before. So now, again, the definition is abstract, but let me just say what a set is. A set, really, it's just a collection of something. It's a fancy word for a collection, like a collection of objects, for instance. A collection of objects, that's what it is. For instance, you can have a set of numbers. You can have a set of letters. You can have a set of almost anything, really. The book actually goes into a lot more set theory than I think that it should. So, not to say you can't handle it. With sets, we like to use curly braces like this to denote them. To denote a set, that is. And again, what we do with sets, we list the elements one by one with commas. We don't list an element more than once, though. In other words, in a set, you're not going to have repetition. There's a lot more to set theory they do in the book, but this is really, for sets at least, this is what I'm going to do only. It's actually what we'll see by, when you list the elements one by one, it's actually what they call the roster method. Like the class roster, right? You have everyone listed one by one. It's really the same idea. Okay, now the fun part. So what exactly is a function? Well, again, this is abstract, so bear with me. Here we have a set, capital X. The circle is denoting it. It's not really formal notation, but that's what I'm using here. Usually we use capital letters like this to denote sets. So we have another set here. Well, a function, little f, from a set capital X to a set capital Y, from a set X to a set Y, it's a rule that assigns to each element, little x from capital X, exactly one element, little y from capital Y. So again, a function basically is taking each element from the first set, each little x that is, and assigning it to one element only in capital Y. That's what a function is. It's a rule that takes each little x from the first set and assigns it a unique element from y. And the fact that it's exactly 1, that's very important and very useful. You can almost think of a function as like a machine. From the first set, you have the inputs, things that go into the machine. For each input, right, you get only one output. For each element, little x, the function f is assigning it to one element only in the second set. Okay, that's probably confusing. I understand that. If I misspoke before, I'm sorry. I don't think I did though, but let's keep going though. It will make sense when we do examples. But again, for now, you could think of a function as like a machine. For each input, you get one output. Okay? Now, here's some terminology with functions. The first set, right, where these little x's come from, things that go into the function, right? The first set here, we call that the domain of the function. All the elements in the second set that come out of the function, that are assigned to elements from the first set, that's the range of the function. So if we go back to that machine analogy, all the input for the function, all the things that go into the function, that's the domain. And all the things that come out, the output, that's the range. That may not be the entire set Y though. It could be, but it doesn't have to be. And the whole point with a function is you want to somehow represent that rule. You know, how do you make the output from the input? What do you do? Well, there's many different ways of achieving that. One way is correspondence diagrams, which is actually what I drew here. With a correspondence diagram like this, where the first set, your domain, you list the elements one by one like so. And for each element, you draw an arrow into the second set, Y, into the output. So this is our first set, capital X, right? We list the elements. Here's our second set, Y, right? And to actually define the function, we use arrows like this. So 1, right? We're going to send that to 2. So using these arrows, we define what a function is. So the function is taking 1 and assigning it to 2. That's what this arrow is saying. 1 is our input, 2 is the corresponding output. Here, 2 is our input. The function is sending that to 4. 3 is our input. What comes out of the function is 6. So when 3 goes into the function, the output is 6. And 4 goes in, 8 comes out. So in this case, Y, all of Y, is the range. But normally that doesn't have to happen. We do have a function mostly because from each element in the first set, from each element, we only have one element in the second set. In other words, for each input, you get only one output. Or with these arrows, from each element in X, one arrow comes out. Here's another example. The same sets, X and Y. The function is a little bit different though, because now 1, it goes into the function, but 1 is assigned to 8. 1 is assigned to 8. 2 is assigned to 2. So again, a function is like a machine, right? Number 2 goes in, and number 2 comes out. 3 goes in, 4 comes out. Here we have 4, right? 4 goes in, 6 comes out. But again, each arrow from each element in the first set, the domain, from each element, there's only one arrow coming out. That's what has to happen in a function. Are there any questions so far?